Hello, this video is a submission for the facial animation assignment. For the first part, we start with the weight sliders. Here on the left, we have a list of 24 blend shapes. They initially start with all of the weights set as 0, but as we change the weights, the shape of the face will change. For example, if we increase the left puff, it's on the right here because it's like mirrored, and we can, for example, make it open its jaw, make it close it again, make it close its left eye, make it open it again. It can wrinkle its nose, we can bring it back, and by manipulating these different weights we can get different emotions. For example, we can make it smile a little, and we can make the other side a bit sad. So that's how the weights are manipulated using the weight sliders. So this basically can be made by having one neutral expression here and having 24 expressions with 24 weights. We are able to manipulate each weight. So we have one weight per expression, and then we take the difference between each vertex in an expression and the neutral expression, and we multiply that by the weight, and then we add the summation of all of these to the neutral face, and we get a certain facial expression. Now in the code, we can see that here. So basically, this is our B matrix that has all of our blood shapes, and this is, the differences between the blood shapes and the neutral face. And this is the weights that we have, and this is how we get it, and we add it to the neutral expression, and this is how we get the final one. The progression from that point was to make an animation sequence. So we have a list of 24 weights that's repeated around 250 times, and if you make them happening in order, you will get this animation. And it keeps looping. So in the code, this happens here. So as long as this key is pressed, I have the animation keyframe, and I keep get the module of that over 250 because we have 250 frames, and I keep increasing the frame every time. For the next part, we need a vertex picker. A vertex picker would be able to pick a vertex from a mesh from wherever you click. This is like a demonstration of how it works. Okay, so the code that makes this happen is basically explained here. So we first get the z buffer value from the point where we clicked, and then we would go and use that with our x and y coordinates from the screen to unproject it. So now we have a point in our mesh space. However, we don't know exactly where does it, like which is the closest vertex to it. So we search each of the vertices until we find the one that's closest to it. And that's our new position of our vertex picker. So we translate it there. Now for the direct manipulator part, we can choose a vertex, for example here. We can choose a vertex and we can move it. So this makes it smile. And we can choose a vertex here, move it here to make it start to close its lid. So depending on the movement of the two picked vertices, you will have a different effect. So this makes it close its eye completely. However, sometimes if we do make big movements and our code is not able to solve for all weights of B, for example, like this, we will get unpredicted results. The weights have been clamped to always stay between 0 and 1. So, yes. Now, the direct manipulation is enabled by this code. So basically, we have two sides, right-hand side and a left-hand side of an equation. They are better explained in the slides. So this is the left hand and this is the right hand. And alpha and mu are constants and they're suggested by a paper. So alpha would be 1/10 and mu I think is 1,000th. I is the identity matrix. W is what we're solving for, which is the vector of weights. So B bar would be a matrix containing the same elements that the array B has. However, it's just the ones that are associated with our vertex picker. So the 2 points, the constraint and the picked vertex, they would go here from the vertex B. It's from the matrix B, and that's B bar. This is then transposed and multiplied by itself and added to this matrix. So that's one side, and for the other side, we take the difference between our point and our constraint, and then we multiply it with the transpose of B, and we add to it alpha weights. So this is here extend the code. Here's alpha, here's mu, here's building B bar. Then we transpose B bar and multiply it by itself and add to it mu multiplied by alpha multiplied by the identity matrix. And then we add values into M and M node, and then we get the difference between both vectors, multiply that by the transpose of B bar, and add the weighted alpha. So that's all.